So here we're starting what we would call real electrochemistry. It's the application of thermodynamics or thermodynamically favorable cells to use electricity to do some work. So when we say something's thermodynamically favorable, that means that it releases free energy. In a redox reaction, we think about either gaining or losing electrons, losing for oxidation, gaining for reduction, and it becomes electrochemistry when we're thinking about those electrons flowing to doing something very specific. So oxidation reduction is still a transfer of electrons, but when we make those electrons flow through a wire or through a solution even, that flow is called electrical current, and it can be measured as how many electrons are passing per second. When you take physics, you think a lot about voltage, current, and resistance. Here, we're really focusing on the electrons themselves and why they are moving. When the two substances that are doing the oxidation and reduction are directly in contact with one another, the electron goes directly from lost by the oxidizing object, gained by the reducing object. But if we physically separate them, then we make the electrons flow through a wire or through some sort of outside object, we create an electrochemical cell. If I were to put zinc in a copper solution or copper in a zinc solution, I would see a reaction that would exchange electrons. But when I separate them like this, that is an electrochemical cell. So we'll come back to this one a lot as an example. But there's some real important key terms we need to know. Just like we have Leo the lion for oxidation and reduction, there's some different terms that we'll use here. So electrochemical cells are classified as whether they are thermodynamically favorable and produce free energy, or whether they are thermodynamically unfavorable and require it. So they are called voltaic or a galvanic cell. If it's favorable, that's what a battery is. It's producing electrical energy. Electrolytic cells require free energy to be put in or require an electric current. That drives the reaction forward, often doing a process called electrolysis. In these electrochemical cells, we have oxidation and we have reduction, but we separate them. That's what allows the electrons to flow through the wire. So we have our two half cells. One is an oxidation half cell, one is a reduction half cell. And within those cells, or within this, we have a piece of metal that serves as an electrode, a place through which electrons can flow. That electrode has to be conductive. It has to let electrons flow through it. And very often, the electrode is a part of the reaction itself. It's a metal that's either being oxidized or reduced. But sometimes we could also see a non-reactive metal, an inert electrode. Platinum is often used as an electrode, and we'll see that in some examples. But when we're doing this, we've got some terms that we need to know. And there's some good mnemonic devices, just like Leo the lion. Oxidation occurs at the anode. So we have anox here. I'm going to color code kind of throughout the rest of this electrochemistry with these same colors, but our vowels go together, ox and an. And then we have a red cat. Reduction occurs at the cathode. When this is happening, our electrons are flowing. They are flowing from the thing that is losing them, the oxidation, or the anode, to the thing that is gaining or reducing them, the cathode. So we often think of this as a fat cat, from anode to cathode. And we can apply all of that up here. The zinc is being oxidized and is therefore the anode. The copper is being reduced and is therefore the cathode. The electrons are being lost here and they're flowing, and the electrons are being gained here as they flow to it. We can also see that the zinc is changing from atoms to ions, and the copper is changing from ions to atoms as we're gaining and losing those electrons. If we are looking at this, we have an equilibrium or a back and forth in terms of what's gaining and what's losing. The position of the equilibrium is determined by K, by delta G, and by what our electrodes are. So we're always very cognizant of what is oxidized, what is reduced, and which way our electrons are flowing, which is why this idea of anode, cathode, and a fat cat is super important.